Welcome to The Explainer. Today we're going to pull back the curtain on something that's quietly powering a ton of modern medical devices. We're talking about the elegant software at the heart of biomedical signal processing, the digital filter.
So here's the game plan. First, we'll tackle the fundamental problem of just how noisy medical data can be. Then we'll unpack the surprisingly simple tools we use to solve it. After that, we'll compare the two major design approaches, see a filter in action finding a heartbeat, and finally we'll zoom out and look at why this technology is such a massive deal. All right, so let's jump right in. You see, every single medical signal, whether it's from an ECG monitoring the heart or an EEG reading brainwaves, starts with the exact same core challenge. How do you separate the vital, life-saving information from a whole sea of electrical noise?
So, when a doctor looks at an ECG, they see that classic familiar heartbeat waveform, right? The peaks and valleys. But what does a computer see? Not that. It just sees a massive list of numbers, each one representing the signal's strength at a tiny slice in time. And that's the key difference. A machine doesn't see a heartbeat, it just sees data that it needs to figure out.
And that list of numbers? That's what we call a digital signal. Think of it like this. You're taking a super fast series of snapshots of the original smooth signal, say 200 times every second. This string of numbers is the raw clay that our digital filter is going to mold. But here's the really tricky part. The most important piece of that signal, that big, sharp spike called the QRS complex that shows the MAME heartbeat, is actually swimming in a sea of other waves and a whole lot of noise. And the real kicker? A lot of this noise from, say, a muscle twitch or the patient just moving around is in the exact same frequency range as the signal we want. So how in the world do you pull the good stuff out? So how do we untangle this digital mess? You'd think it takes some super complex, high-tech process, right? Well, you'd be surprised. It all boils down to just three really simple operations.
And this is what's so incredible about it. We're not talking about some specialized, exotic piece of hardware. The most advanced filters are built using the exact same basic tools that your home computer has. It's all about having the right recipe, the right code.
And these are the magic ingredients. Storing a number for just a moment, multiplying it by some other number, and adding two numbers together. That's literally it. By combining these super simple functions in clever ways, you can build filters that do these incredibly sophisticated things, shaping that noisy signal into something perfectly clear. Okay, so we've got our basic toolkit. Now, when an engineer sits down to build a filter, they usually go down one of two main paths, two different design philosophies, and each one has its own distinct pros and cons. On one hand, you have FIR filters. Think of them like a straightforward assembly line. Data comes in one end, gets processed step by step, and goes out the other end. They are super predictable and always stable. Then you have IIR filters. These are a little different. They use a feedback loop, kind of like a quality control check that sends information back to an earlier stage. This makes them way more powerful and efficient, but there's a catch. If you don't design them just right, they can become unstable. All right, now for the really cool part. Let's put this all together and see it in action. We're going to watch how a carefully designed sequence of these digital filters can take a totally noisy ECG and pull out a clear, unmistakable heartbeat. We're going to walk through a classic, tried-and-true algorithm. You could think of it like a multi-stage process where each filtering step transforms the signal, sculpting it and making that QRS complex stand out more and more from all the background clutter. Okay, so here's our starting point, the raw, messy, unfiltered ECG signal. You can kind of see the heartbeat in there, right? But it's buried under all this other junk. You've got low-frequency drift making the baseline wander and high-frequency noise from muscle activity. It's a real mess, and a simple program would have a terrible time trying to find a reliable heartbeat in there. First up, we hit it with a bandpass filter. Think of this like a bouncer at a club. It's designed to only let frequencies in a very specific range, right around where the QRS complex lives, get through. Everything else gets rejected. And just like that, you can see a whole bunch of that low and high frequency noise is gone. It's already so much cleaner. Okay, next step is a bit of digital calculus. We use a differentiator, which is just a fancy way of saying we're looking for the steepest parts of the wave, which of course is our QRS spike. This makes it much more prominent. Then we square the whole thing. This does two brilliant things. It makes every value positive, and it makes those big peaks even bigger, really making them pop while shrinking the smaller stuff. And for the final touch, we use something called a moving window integrator. This basically smooths everything out by summing up the signal's energy over a tiny window of time. What it does is transform those sharp, spiky signals into these beautiful, clean, rounded pulses. Now that is something a computer can easily spot with a simple threshold.
And here's the payoff for all that work. Look at that improvement. The peak of that final pulse is now more than 10 times higher than any of the leftover noise. It's gone from a fuzzy, maybe that's a heartbeat, to an absolute, undeniable yes. Finding and counting the heartbeats now is a piece of cake for the machine.
Okay, so that was a neat trick, but why does this actually matter in the real world? Well, this whole software-based approach, when you pair it with the absolute explosion in computing hardware, has literally changed the face of modern medicine.
You've probably heard of Moore's Law, right? The idea that the power of a computer chip basically doubles every couple of years. This incredible, relentless, exponential growth is the engine that made all of this possible. It gave us the sheer processing horsepower to run these sophisticated filter algorithms in real time on tiny, low-power chips.
And the impact has just been huge. I mean, it's why we can have portable, battery-powered medical monitors that patients can wear at home. It's what allows for complex analysis to happen right there on the device, instantly. You get these incredible machines, like an entire ECG interpretation system that can literally fit inside a briefcase. We essentially took a massive, expensive hardware problem and turned it into an elegant, efficient software solution. So that leaves us with a pretty amazing thought to end on, doesn't it? As our digital toolkit just keeps getting more and more powerful, the potential for a few clever lines of code to diagnose, monitor, and even treat disease, well, we're really just scratching the surface. What was once science fiction is now just an algorithm waiting to be written.